All right. So in this video, we're going to talk about, start talking about real gases, okay, and how they deviate from ideal gases. So in this video, we're just going to talk about what is a real gas, how does it deviate from an ideal gas and such. And later, we'll talk about what are the equations of states that one uses to describe real gases, right? Similar like that gas law is the equation of state for an ideal gas. What are those similar types of equations for a real gas, okay? So a real gas, right, breaks some of the rules that an ideal gas behaves, right? And one of them is, right, that for an ideal gas, there are no intermolecular interactions. For a real gas, there are, okay? And these intermolecular interactions could be attractive, okay, which is given in sort of this gray region, you know, in this curve over here, right, or repulsive in this kind of maroonish region on the left, right? And those interactions can be those attractive or repulsive, and depending on whether or not those intermolecular interactions are more attractive or more repulsive between the molecules can greatly dictate how it deviates from an ideal gas. Okay? And one way we measure this deviation is through what is called the compression factor Z of a gas. So the compression factor Z of a gas is given by this equation here. Okay? It uses the molar volume. The molar volume is just the volume divided by the number of moles. Okay? That's all it is, the molar volume, right? So given this relationship, okay, what would Z equal for an ideal gas? Right? If I look at the definition of Z, right, if I say plugged in pressure in here, right, I know for an ideal gas, P equals V, or sorry, RT over the molar volume, okay, because it's N divided by volume. You simplify that to the molar volume, okay. So this is what the ideal gas equation is in terms of molar volume and pressure, okay. If I plug that into this equation, right, we see the molar volume cancels out, R cancels out, and T cancels, right? Everything cancels, right? So Z for an ideal gas is equal to 1, okay? That's all it is. Z is equal to 1 for an ideal gas, okay? Now, for a situation where Z is greater than 1, okay, right? If Z is greater than 1, okay, another way this Z can be rewritten is Z can be written as the molar volume of your gas divided by the molar volume of an ideal gas, okay? So you can rewrite this equation, right, in terms of essentially, right, the molar volume of an ideal gas is equal to RT over P, okay, right, just using the ideal gas law, right? So if I plug in that into this equation here, I will get the compression factor Z is related with the molar volume of my gas divided by the molar volume of an ideal gas, right? So looking at that way, we'd say, okay, if Z is greater than 1, that means this numerator is larger than the denominator, right? That means that my molar volume is greater than that of what an ideal gas would be, right? And so if your molar volume is greater than that of an ideal gas, that means your gas is expanded more, right? It wants to be further apart from each other, right? Atoms and molecules do not want to be near each other. They want to be further apart, so it takes up more space, okay? And so that means that repulsive forces dominate, okay? Right? This implies, so if Z is greater than 1, that implies that repulsive forces dominate, okay? Right, and then if Z is less than 1, it's the exact opposite effect, right? Now your gas is taking up less space than an ideal gas would, and that's because the molecules that make up this gas are attracted to each other, and so they want to stay more near each other instead of bouncing off walls, and so it makes less collisions, and it's not going to be taking up as much volume as it needs to because things are more attracted to each other and condense down a little bit because of attractive, favorable interactions, right? And so these ones have attractive, right, forces dominating. Okay. right? And so again, if we look at the compression factor of any gas, what you'll find, right, is on the x-axis here we have pressure. Okay, so this is the pressure of the gas, right, versus compression factor. What you'll find at low compression factors, okay, or low pressures, your compression factor is often less than 1, right? Often have some sort of compression factor here. That's less than 1. So it's not really marked here, but this is equal to 1, right? The ideal gas value is equal to 1, okay? So you often have cases where things are less than 1 because you have attractive forces dominating at these low pressures, okay? But when you get to higher and higher pressures, everything starts to have a compression factor greater than 1, right? Everything starts ending up in this region where it has compression factor greater than 1, and that's because repulsive forces are dominant, right? And that makes sense, right? When things are at low pressures, things are spread out a little bit more, stuff has more room, right? And so these attractive forces can interact, these molecules interact with each other attractively, right? And kind of bind to each other a little bit and reduce the compression factor. But once you get to higher and higher pressures, eventually you're going to compress this gas so much that stuff just doesn't want to be near each other anymore. No matter how attractive their intermolecular forces are, okay, eventually you're going to run into this repulsive region if you press the gas down enough, increase the pressure enough in the system, okay? And so that's why everything eventually has a compression factor greater than 1, just because eventually you're squeezing the gases too tight that they really don't want to be near each other. Okay. So finally, let's talk about another example of differences between ideal and real gases, okay? So this is an isotherm for, I believe it was carbon monoxide, CO, okay, right? So these are different isotherms. So for example, in this top isotherm here that I'm outlining, right, this is essentially what an ideal gas kind of behaves like, right? Because for an ideal gas, pressure is proportional, to 1 over the volume, right? Right. There's proportionality constant RT. Or NRT, yeah, NRT, right? That's the proportionality constant, right? But not very important, right? So the system kind of behaves like an ideal gas, and it's roughly P over V, okay? But at lower temperatures, right, you kind of still have this ideal behavior at points A and B, but then you reach point C, okay? Right, and what happens after you reach point C is as you reduce the molar volume, right, as you start compressing this gas more and more, the pressure of the gas does not change anymore, okay? Well, what's happening here is we're having a phase change, and I'm going from a gas phase to a liquid phase, okay? Right, and so what's happening is at C, I'm actually at a molar volume and pressure that gives me this liquid gas equilibrium, and I'm undergoing a phase transition at point C. And as I compress the gas, I force more and more gas molecules into the liquid phase, okay, until I eventually reach point E, where now all of my gas is condensed into a liquid, okay? And then after point E, I just go to point F and such, and now I'm trying to compress a liquid, and so any slight decrease in volume is going to have a very large increase in pressure, okay? Right, ideal gases would never, ever condense down to a liquid because they have no intermolecular interactions, so there's no reason for them ever to form a liquid, right? And that's obviously not the case for real gas, right? And so it's under these very small molar volumes, very high pressure systems that things deviate the most from ideal gases, okay? And that's it for this video on real gases. In the next set of lectures, we'll talk about the equations of states of real gases.